This podcast is presented by SCHOTT, with over 130 years of experience delivering innovative, high-quality products. SCHOTT is the global leader in specialty glass, glass ceramics, and other innovative materials. With a direct presence in over 30 countries, the company is a highly skilled partner for several high-tech industries, including defense, semiconductors, data communications, optics, energy, automotive, aerospace, and healthcare. One of SCHOTT's key goals is environmental protection corporate-wide, and it is committed to being the first specialty glass manufacturer in the world to be climate neutral by 2030. Thank you again to our sponsors at SCHOTT for helping us present this podcast to you. Welcome to Emerging Tech Horizons. I'm Dr. Mark Lewis, the Executive Director of NDIA's Emerging Technologies Institute. And on today's segment, we're going to be exploring all aspects of digital twinning. And to help us do that is Steve Carlson, who is a 30-year veteran of the electronics industry. Steve has been focused on aerospace and defense solutions for at least the past 10 years. His current research interests are in hardware and system security, supply chain assurance, electronic warfare, systems verification, digital twinning, which will be a primary topic of conversation in this segment, advanced semiconductor design processes, and approaches to parts obsolescence. Some career highlights for Steve. He's had a number of diverse positions at Cadence, including Aerospace Defense Security Solutions, Aerospace Defense Functional Verification Solutions. He's worked in the Office of the Chief Technology Officer on advanced nodes, low power, mixed signals. He's spent about 20 months. He's been involved in philanthropic work. He's done high performance data path automation, low power mixed signal product management, digital solutions, high level synthesis through sign off product management, and front end design product management head, including synthesis, test, and equivalence. Steve has been a principal investigator on numerous programs, including some from DARPA. He's presented in numerous DoD-centric conferences, workshops, forums, as well as co-authoring articles related to defense electronics development. So, Steve, first, once again, thank you so much for joining us. Thanks for your work on behalf of national defense.
Mark, thanks for having me. Really a pleasure to talk with you.
So Steve, if I could start us off, I went through a little bit of your career, but could you elaborate on your background? Tell us how you wound up doing the work that you're doing. What was the path that led you there? And maybe fill us in a little bit about the primary activities that you're involved in right now.
Sure. So I'm a third generation Californian, and went to school here until I went out to Colorado and got a couple undergraduate degrees, electrical engineering, computer science. I worked at United Technologies Microelectronics Center in Colorado Springs for a year, and then went back to grad school. Then came out and started in Silicon Valley, and that's the area that I grew up in, actually. And I worked at LSI Logic, and then went on to a few startups that were successful. And one of them ended up being acquired by Cadence, where I've been since 2004. And as you have read earlier, I've been kind of across the organization, so I have a background in many different domains, and been able to apply that broad experience and knowledge base in the defense domain for the past 10 or so years. So it's been a lot of fun so far. More recently, been involved in programs related to big defense programs in aerospace and undersea kind of programs.
Very good. Could you tell us a little bit about Cadence, writ large?
Yeah, so Cadence is sort of a medium-sized company, about 10,000 employees. I'm not going to quote any financials or anything; might get in trouble. We started as a design automation company for chip designers, and over the years, we've kept expanding the capability sort of up the stack towards the system. So we have a full packaging set of design and analysis capabilities in PCB. And then more recently, we've been adding systems analysis capabilities in thermal, EMI, CFD, the computational fluid dynamics kinds of capabilities. So that's the direction that we're heading, is sort of computational software for microelectronics centered systems. And we've even started moving out into the healthcare area and other sort of computationally intensive software endeavors for things like molecular modeling for therapeutic solutions.
Very, very interesting. So now if we could shift gears, focus on digital twinning. So I think many of our listeners have heard about the importance of digital twinning. They know the department is moving towards this whole concept of digital twins. They probably heard about how it's going to help reduce acquisition lifetimes, cycle times, but many of them may not be completely aware of exactly what digital twinning is. So could you explain it? What is it, and why do we want it?
Yeah. So it's been interesting. So we've done a lot of work over the past 4 years in looking at sort of the microelectronics centric issues and getting folks to adopt best practices. And that includes the use of digital twins. It's confusing because anybody you ask is going to probably have a slightly different interpretation of what a digital twin is and what the capabilities and limitations are. And I just came across a really nice white paper that described, sort of the physics-based modeling and digital engineering aspects of it, but it really didn't cover the elements centric to successful microelectronics design at all in it. It really focused, more on the physical manufacturing aspects. And so the point being, it's kind of an overloaded term with many different meanings to different folks. What I wanted to talk about today is sort of the microelectronics centric view, and why that's important in the DoD is that most systems being developed and being serviced in the DoD today have an awful lot of microelectronics in them, and in fact, you could say they're the central part of the system that makes everything else work in many cases. And so, getting that right and doing that efficiently is of the utmost importance in being able to field new capabilities for the warfighter more efficiently. In the microelectronics world, it's very specifically there's a whole abstraction ladder that adds to some of the confusion for folks. But kind of the heart of what makes things work in the commercial world and enables best practice first pass success flows is the use of a hardware accurate digital twin. Right. And so this is different than the abstraction of, instruction set architecture kinds of abstractions and things. It's accurate down to the bit level, clock cycle by clock cycle. And the other key aspect to it that enables you to do other types of analysis besides functional is being manufacturing correlated. And we get these from the foundries, from the manufacturers, we get these things called physical design kits that have been correlated to the manufacturing process to get the predictability that enables first pass success. And this is key for being able to predict performance, power, thermal, EMI emissions, etc.
So how is that different than previous practice? Because we've done computer simulation, we've done other modeling and simulation, obviously, for many years. What's different now about digital twinning?
There's actually a lot different, and in particular, let's start with the verification practices. So that's a 2 to the n kind of a problem where looking at the number of state bits within a design, and so it's grown hyper exponentially. The difficulty of the problem, you can never really verify everything in a multi-billion transistor design, so you have to do the best you can in the time and resource allotted. And there are some specific methodologies and technologies that can be applied in unison that enable you to do a adequate job to get a new product to market, like a cell phone or other complex networking equipment, etc., and not have to respin the design multiple times. In contrast, what I see in the defense industry base is they have not adopted these new technologies related to verification, and they still rely on doing physical prototypes and then looping back into the design. And they'll do that. I've seen one FPGA design that went through 18 iterations before it was, they declared victory on the design. And you would never, ever be able to do that in the commercial industry. So a lot of the work that we've done is in the past years is just trying to move the defense industrial base up to commercial best practices in verification. In the design realm, the digital twins for commercial designs, the back-end design, so the synthesis, place, and route, the realization of the design and handoff to the manufacturer has become a largely turn the crank process thanks to that manufacturing correlation that goes on before any end user is given the process information to undertake a design. So the synthesis, place, and route process through sign-off is very rigorous and a well-trodden path. It's not always easy, depending upon the goals that you have for the performance and power kinds of metrics. But there is a well-trodden path, and it does lead to first pass success very reliably at this point. You just can't afford to miss Christmas in the commercial market, or you'll go out of business, or people have to find new forms of employment if they don't. And we just have not. I would say in the defense industrial base, they've sort of shied away from the use of custom silicon at this point, and have relied on commercial off-the-shelf parts to too large of a degree at this point. And it's difficulty to meet some of the new swap goals requirements that are being set out for some of the new systems. And so we're going to have to reintroduce this expertise and the rigor that is available and has been shown to work. So, the readiness level is extremely high at this point. And we just need to get that back into the industrial base. And that's what we've been working on. Digital twins are a key to that in reducing the risk of achieving first pass success and what many folks perceive to be, the too costly a custom microelectronics path. Maybe I'll pause there and let you ask.
No, that sounds all good. So it sounds like broad application across the entire DoD. Is that correct?
Yeah. So there are pockets of expertise that are growing, but they're pockets. It's not there has not been the broad adoption of these commercial best practices at this point, and that leads folks to the guardians of the status quo, if you will, those folks that know how they've designed in the past, and they're going to continue to do it, and there's a predictable outcome. And
so Steve, it would be safe to assume that there are applications across the Department of Defense for digital twinning.
Absolutely. So in the general case of digital twins, not particular to microelectronics, any system would benefit from having a digital twin. And that's, across the life cycle of the system, from its planning and design, through the initial field tests and throughout the life cycle. And then when you start looking at upgrades and DMS, parts obsolescence kinds of issues, you could benefit from digital twins across that spectrum. Yeah, so absolutely.
I'm especially interested in the parts obsolescence part of this, because the department is spending so much money on end of life buys and trying to as I say, spending sometimes billions of dollars to fill supply cabinets with parts that are already obsolete. That's why they're being discontinued. So could you explain a little bit more detail how would digital twinning address that issue?
Yeah, certainly. So for microelectronics, I think there's a good path forward, and that comes from having that hardware accurate manufacturing correlated digital twin. And we talk about the digital twin, that package of intellectual property that needs to be delivered. it includes the description of the design, but also the requirements, and getting a hold of all the constraints and analysis routines that were used to analyze the design during its design. So the semiconductor or microelectronics that were being designed, right? And once you have that package, you have all of the information that you need to reproduce it and verify that it is a viable replacement for the mission set that you've verified it under. So, more specifically for microelectronics, it's getting all the hardware accurate. So what we call the RTL code, that register transfer level description, and then those get synthesized into more manufacturing specific representations. We call the gate level net list, for a particular process node. And then there's constraint files and verification files that go along with that give you the speed, the power, etc. So when you run into a parts obsolescence issue, what we can do then is take that hardware accurate description and then resynthesize for an available technology node, and then use that same verification environment to see that the behavior matches one for one. And we've done this on a bunch of designs. One of the ones I can talk about is a commercial avionics application, and we created the digital twin using our emulation technology, and then hooked it up to the existing prime mission equipment, and then ran through a series of verification tests, actually billions and billions of cycles, and verified that in lockstep, the digital twin matched the existing equipment. And the FAA took a look at what we were doing and said, this is the most highly verified microelectronics we've ever seen. And they got rid of a lot of the requalification requirements. Of course, you have to do some flight tests and other things, but a lot of the other requirements, the certifications, we were able to step through because we've had shown to such a great degree the match between the two. So the key for the DoD is to get that IP package, right? And this is something, the government purpose rights. This isn't, to replace it, but when you get a no bid or the expertise is gone at a contractor, then the government may have no recourse but to seek another supplier or do some work themselves. Well, if you're equipped with that IP package, you have everything you need in order to be successful to do that. And that's probably the hardest part about the parts obsolescence, the diminishing manufacturing source issue, DMS, is that IP rights thing. And so folks will say, well, I've got my IRAD money, in that IP, I'm not going to give it to you. And this IP rights needs to be negotiated upfront and exercised more often so that you can take control of these obsolescence events and not be a victim to them.
So a couple of follow-on questions. You gave us the example of the avionics system that benefited tremendously from digital twinning. Do we have some other success stories?
Yeah, so I can talk sort of, application area. So atmospheric monitoring system for submarines, designed in the 1970s, produced in the 1980s, and being used, carried forward on some of the newer platforms as well. We've got an electronic warfare system in a fighter plane. We've got the core computer on one of the advanced weapon systems there. We've got, I guess, 2 other EW platforms that we've done this work for. So, we've Cadence itself has done a number of these using these techniques over the past 4 years or so to, first time success on all of them so far. Knock on wood on that we keep the record going. But, It's not surprising because of all the work we do in the commercial market and that first pass success that you get.
So, okay, so you also mentioned the issue of securing IP rights, and that leads to the question of what are the barriers? Are there other barriers to implementation, and if so, how do we get past them?
Yeah, so understandably, the contractors want to protect that IRAD money, that internal R&D money that they spend, and keep it as a differentiated investment that they make. Nonetheless, the government, is paying for the development of the system, and they have access rights to that, and just that has to all be agreed upon so it doesn't turn into a legal battle later in the program when so many folks have moved on and don't understand the situation. So those guardians of the status quo, that's kind of the IRAD argument has been a part of that. The thing that we're running into, so we've gone through and kind of explained to many folks, the education cycle that's been going on for almost half a dozen years, I guess, that how this can work and overcoming all the technical objections and raising risk if I change my design practices and things like that. And we've shown them to the contrary. It doesn't have to be. It can be an additive kind of thing, and it's going to give you better success faster. But if you're paid to fail, right? If I get to respin my design and get paid again, that's the high margin part of the business. So so that's in one situation last week, we had made so much progress that we ended up not arguing with engineers anymore, but they put the lawyers on it. and
right,
so
right.
it's there's
no insult to the lawyers in our audience, by the way. Yeah, no, go understood. It reminded, there was the old Dilbert joke about where the boss tells Dilbert that there's going to be a bonus paid for everyone who finds bugs in their own software.
Yeah.
And so all the engineers are putting bugs in their software. So same idea.
Yeah. So another key issue is this, the color of money, right? And the way that the acquisition and system sustainment buckets are broken down. And it's the folks that are the front end of the acquisition process aren't incentivized to make sure that the operations and sustainment part of the budget is going to be, most efficient over the years of service. And so, things like if they have to pay some extra for the IP rights up front because there is a substantial IRAD investment involved with that needs to be considered, they're probably not going to do that because it increases, their costs up front, and they aren't measured on that, right? They're measured on the cost of just building the first article, not of maintaining a system for 40 years or how long.
So is it safe to say that we not only face technical barriers, but really cultural barriers as well? Yeah. Okay. So I'm interested in your opening remarks. You mentioned applications beyond the Department of Defense, and I wonder if you could elaborate on that. What other industries' applications could we use the digital twinning idea, and maybe take lessons learned from DoD and apply them more broadly?
Well, I think in this case, it's actually the reverse, where we're taking lessons learned from the commercial industry and applying them to DoD. So again, I'm speaking primarily from a microelectronics centric point of view, and I don't think that there are many that would make the argument that the commercial industry isn't very far ahead of what the standard practices are within the defense industrial base. In fact, the CTO of AFRL, the research labs, puts it about a 20-year gap in what he has seen. He's has done work in the commercial world and has been at the Air Force for a bit here, and so there is a lot of room for improvement without getting too far over your skis. There's a lot of safety in just moving forward. But with regards to the applications, it's virtually everything that's got microelectronics in it today, they use a form of digital twinning, this hardware accurate digital twinning during their design process. Every one, right? So if it's a networking, if it's your cell phone, cameras, your Amazon Echoes, everything that's got a chip in it, these guys are digital twinning. And I would say one of the most interesting things that's been transpiring is the move to putting the chip in the context. So virtually putting the chip in context before you manufacture as a part of the verification. Used to be you could write, directed tests and look at the different features of the hardware, test them all out. Because the hyper exponential nature of the verification problem, it's really about, you need to get a better model of the context. And so folks use the virtual model of the hardware and then load their software stack on top of that. And so the hardware is all verified within the context of the software. So the cell phone makers, one of them in particular, likes to make sure that they can load and run Angry Birds before they ever send the chip off to the fab. Right. The other piece to the modeling the context is the physical context. And so looking at the packaging and the enclosures and airflow, cooling kinds of considerations, making sure that those are all modeled with that software running, and then looking at what the thermal conditions are going to be under, heavy loads, various use cases of the system. And then, there are performance limiting frequency and voltage scaling kinds of things that go on if things heat up too much. Well, you have to have an accurate model of the environment, the enclosures of the hardware to really do a good job of that and really be able to walk that fine line of performance and reliability.
Very good. Do you think there's hope that the adoption of digital twin practices can help reduce the cycle time for acquisition?
Absolutely. So, so many respins through that prototyping lab and back. So in the commercial world, you're counting on first pass success to be able to meet the market, and the rigor that has been built around the process now is very repeatable. It's very transferable, and there's no reason why those best practices shouldn't be used in the DoD. For microelectronics, I think it's very clear that there's a lot to gain, and it's because we have this manufacturing correlation that's happened. The complication with DoD systems is that there's a lot of physical parts to many of the systems that will benefit from digital modeling, but they don't have that manufacturing correlation, right? And so the manufacturing correlation is actually done through those physical prototyping loops, but we can reduce those, with better modeling and characterization and correlation between the manufacturing process and the modeling that's going to be used up front, like we have done for microelectronics. But certainly, so people will talk about I'm using multi-physics modeling. Well, that's good, but you need to make sure that the nuances of the manufacturing process are modeled correctly with the physics, right? And that's the part that's more difficult because there's these one-off first article kinds of situations. And that's why you have to do rocket engine tests and things like that. And you find failures and you go back to the drawing board, is because they have not closed that loop sufficiently.
Right. No, that makes absolutely perfect sense. Steve, I'm going to let that be the last word for this podcast. It's been an absolutely fascinating conversation. So the power of this capability, the implications across the department, across the industry. The ability to reduce cycle times, absolutely critical, and an emerging technology. So thank you for explaining this to us. Thank you for joining us, and thank you for all that you do for the department.
Great. Well, thank you very much for having me, Mark. Really enjoyed it.
I want to take a moment to highlight ETI will be hosting our upcoming Emerging Technologies for Defense Conference and Exhibition. It's going to be held at the JW Marriott this summer, August 28th through 30th. Please look for more information on our website. And as always, look to our website for other podcasts and other research products being generated by NDIA's Emerging Technologies Institute.